Thank you very much. Welcome, everyone. Again, I'm Jared Hansen. I am the electronics manager here at RAND Simulation. Just briefly about myself before I jump in. I have about a decade's worth of experience within Ansys tools, mostly in the antenna design as well as high-speed PCB design applications. Today, I'm going to talk about how we can improve PCB reliability using SIwave. Typically when we're thinking about reliability, we think about mechanical reliability, shock, vibration, impact studies, those sorts of things. Today, I'm going to be talking about electrical reliability. So specifically in this presentation, talking about power integrity and what we can do within the tools. So kind of an overview of what we're going to talk about today. I'm going to start out with a really brief introduction into what power integrity is. I'm going to go through some examples. I'm going to offer really an overview of what tools Ansys has at the disposal for users to improve their designs. I'm going to talk about it from a couple of different application standpoints, and then I'm going to go through the workflow. And we're going to talk through really two workflows today, and I'll go into those details a little bit further. So, what is power integrity analysis, and what are we talking about? So, when we have the high-speed PCBs, these complex systems that have multiple clocks, have multiple power supplies, power rails, and many data channels, ICs, on the board, we need to verify and we need to understand how the power delivery network is going to perform and that it meets the requirements of the ICs and the other components on the board. And really what we're talking about here is we're talking about reducing ripple and maintaining a constant voltage to the appropriate ICs. Now, this can be a challenge, especially for a lot of new designers or people that have not looked at simulation and may just use kind of a rule of thumb design techniques, and they're trying to apply those to higher speed signals or more complex boards. So, when we're looking at this, when we're looking at a board and breaking it down into the components, we need to make sure that we're representing everything appropriately within the design, starting from the VRM and going all the way to the active device with everything involved. This includes components, parasitics, passive components, as well as the traces, layers, and pores themselves. So when we're looking at this, if you were to think about this from a hand calculation perspective, it can get really difficult. We're talking about a lot of inductive loops. We're talking about the coupling of many planes, which may modify or influence impedance. And we're talking also about the resistive paths where you have ground loops and your different passive components as well. And so this is really why simulation for power integrity is so important. We have so many things we need to juggle. And the reality is to do that by hand or on the benchtop can be very difficult. Whereas within the Ansys tools, specifically SIwave, we are going to show you that there's a really nice workflow. It's really well built for user experience, and you can get some very accurate results. So here's just an overview of the electronic software. I wanted to bring this up just because we talk about the different softwares, but there are quite a few within the electronics desktop and the other user interfaces. We have HFSS, which is the high-frequency tool for 3D simulation, Maxwell, the low-frequency 3D tool. We have SIwave, which we're going to be talking about today, Icepak, Thermal Solver, which we're also going to be highlighting today. Q3D Extractor is a parasitic extraction tool. And most of these, except for SIwave, are all housed within the electronics desktop. So again, the goal here is that we're going to be talking specifically about SIwave as well as Icepak. In specifics, here's just a general overview of what SIwave is. So we're talking specifically about power integrity today, but there are a lot of different other applications that can be analyzed or discussed using the SIwave simulation tools. This includes looking at signal integrity. This includes looking at EMI and, fully developing and understanding your boards for many different applications and purposes. Icepak, the other tool I'm going to be discussing today, is the electronic CFD tool. So this tool will allow you to simulate your PCB and understand the thermal, as well as if there are any fans involved, the acceleration velocity, as well as how that board may be mapped rather for temperature. So we can go in and assign thermal dissipation values. We can also, what I'm going to be showing you today, is we can take electromagnetic simulations done in SIwave, and we can apply those as the excitations for a thermal solve in Icepak. So there's a really nice transition between the two tools, which allow you to get a very exact result for a thermal simulation. Just a nice, look at the power integrity workflow. We can look at this really in two forms. I wanted to bring up the image on the right because this is what you'll see actually within SIwave. This pops up when you start with a board. It's the SIwave workflow wizard. And the nice thing about this is built from start to finish for power integrity simulation. So you know exactly the steps you need to walk through in order to go from importing in your board to getting those decoupling capacitor values and components to be successful. And what we have, on the left here is really that, walkthrough and what we're going to be discussing in detail today. I am going to take the aside, to talk about DCIR and thermal. I'm going to start with that, and then I'm going to come back into power integrity. Just because, this is something I really enjoy talking about, the multi-physics simulations that we can perform, just simply because not only is it a very strong tool, but it allows electrical engineers to take the information that they know, voltage and current, and power, and translate that into thermal, which is, can be traditionally more difficult for users. And so in this regard, I really like talking about this because the workflow can be so smooth in getting those results. So it adds another level for engineers to be able to discuss with colleagues, to give data to management, so that they are a more overall balanced engineer when they're talking through why they need to make a design change, why something may or may not make sense, and really improving the system overall. Before we jump into that, I'm just going to talk about importing PCB files. So you may be asking the question, well, this tool sounds great, but am I going to have to make geometry? Am I going to have to go into the tool and design my traces? And the answer to that is simply no. If you're already building your boards in most common design tools such as Altium or Cadence, there are ways to bring in your PCBs that you're already getting ready for development. Most commonly, we see IPC 2581 and ODB++. So the difference really here between those importing different types is the quality and the amount of data that comes in. So for example, ODB++ is going to give you those layer, trace, stack up, pad stack information, trace names, differential pairs, all that kind of stuff that you would expect. The one thing, that the caveat here with ODB++ is that it doesn't bring in the information such as passive values. So if you have resistors, capacitors, inductors, those usually default, whereas a file type of IPC 2581 does bring that information into the solver. So it saves you time. There are ways to get around that, which I'll be discussing actually next. But these file types are very common, and they can be quickly generated and brought into the tools. I'm going to talk about component mapping next, simply because the quality of the simulation that we perform is dependent not only on the board geometry that we bring in, but also the quality of the models we use for our components. And what I'm specifically talking about is inductors, capacitors, or resistors. When we're looking at power integrity, specifically inductors and capacitors, ensuring that the values that we bring in are not just those passive information that, the generic passive values. We can actually get into more detail where we can bring in a SPICE or an SNP file, or also known as a touchstone file, which contains that frequency-based data, which represents that capacitor or inductor across frequency. And that's going to be significantly important when we start talking about optimizing those capacitors or inductors over a span of frequencies to verify that the performance of your VRM and your whole system, your PDN, your power delivery network, is properly defined. Now, if you don't have those values, if you don't have those components, can you get away with just the passive? It gets a little bit difficult. And so representing these as SPICE or having a model is important, and that's why Ansys has a built-in library for many inductors and capacitors that you'll find from the major manufacturers. On the right we have a few of those: AVX, Kemet, Samsung. Those are all very common manufacturers, and so properly representing these within your simulation, as I'm saying before, is very important. Once we get, so now that we've gotten past bringing the board in and looking at it and assigning those components, I'm going to start talking about the DCIR to Icepak workflow. So in this case, we're sticking now in that electrical realm where we can assign a voltage source and current sinks to the PCB. So the way that I like to describe this is when you think of the voltage being sourced on the power rail, so let's say, a 5-volt source, and you'll have a set of ICs that require some current to run properly. So we would go through assigning the power rails, and we would then assign the current sink at the components themselves. And this is what drives the simulation. So you don't have to have a lot of information. You don't have to get into the nitty-gritty details of these components to run this simulation. It's very streamlined. And I actually want to show you this next slide here of what the setup looks like. You'll have a drop down of the nets and then the components on those nets. So in this case, we're looking in red. Those are ones associated as either a power rail or a ground. And you can see here when one is selected, the reference designators show up where you can now assign either a voltage source or a current sink. And this is, again, what drives this simulation, which is, again, very easy to set up. And you can now use these results for that Icepak simulation. I just want to show you what this looks like, this right here, because if anyone has SIwave currently, this is something that you can do. Within this, we can export power dissipations. This is the important step to include if you want to perform that thermal simulation. The other thing I just highlighted down below in the bottom left is not only can we perform this with a single core, we can do multi-processing. So with HPC packs, we can use multiple cores to speed up your simulations. We can also address accuracy. So if you're looking for a more refined mesh, within those other solver options, you have the ability to better refine the mesh, the adaptive mesh that's being produced, to ensure that the accuracy is very high. Now I'm just going to quickly jump into what those results for the DCIR study looks like. In this case, I'm showing both voltage and current. So in the upper left, we have our voltage plot here. And on the bottom right, here's an example of current density being plotted, so we can see the flow of current on your device. So this is one that's really insightful if you're looking for current on return paths. So you can see and represent this current and ensure that there isn't, a massive current, a massive amount of current and high current density forming at certain places on your PCB, which of course, once we start talking about thermal, we could be talking about the high thermal events on your board. The other thing that we can see, which I think is very useful, and I know this is a little bit small, but it's there on purpose, is we can see the high current vias. So we can go in and look at the vias specifically and see potentially where there are vias that have higher than normal current. And again, when we're talking about converting this into thermal, this could be where you could see some, higher than usual thermal values. I'm going to take a drink real quick. And the other thing that we can see within the simulation, which I think is extremely beneficial, is the power tree mapping. I know this is a really large image here, but what this is depicting is the voltage and current and the voltage drop from component to component. So we can see here, in a case of a pass-fail, if the ICs, for example, are getting the proper voltage and current that they need, depending on specifications the user sets. So this, again, is a very nice addition to the simulation, because you can go in and inspect this and get a good understanding if you have components that are not being powered appropriately, that may result in some, inspection, some figuring out where the current is going, and ensuring that your designs are being powered correctly. So again, just kind of an overview here, because I got to move a little bit quickly, of the DCIR simulation within SIwave. You can import and set up very rapidly within the tool, and they give you some very detailed results and insight to your PCBs. Now, of course, those electromagnetic values that we're looking at here can be exported and used as excitations for the CFD, the thermal solves. And the other thing that's really nice about this is, just because we're talking about DCIR doesn't mean we're stuck at a single phase. We can do multi-phase simulations. So if you have a complex VRM, we can incorporate that as well, as shown in the image to the right. And you can see within these applications that we can, better represent the power delivery networks on some very complex systems. So now I'm going to jump into Icepak within SIwave. So there is the Icepak standalone tool. It falls both within Icepak Classic and within Icepak for Electronics Desktop. There's also actually one more, which is the one I'm going to be chatting about today, which is specifically Icepak within the SIwave tool. This is a really nice and quick way to get an understanding of your thermal while working in that same workflow of SIwave that you know and love. So what's nice about this is you can do some very quick setups for both conduction and convection. And again, as I was saying before, driving those simulations from the DCIR simulations. What you see on the right here is the simulation setup. There's a lot of very nice and user-friendly, slider bars, which you can then go in and define the meshing detail. Now, of course, if you're looking for some more control over the mesh, for example, we can bring this into Icepak Classic or into Icepak AEDT. There is a nice export. And I'm spoiling a little bit at the end here, but there's a nice update within 2021 R2, which streamlines the process for users that have or use Icepak within AEDT or the Electronics Desktop version of Icepak. So as I was saying, there are also tools for both forced and natural convection. And again, that automatic mesh that can be created from a user-defined slider bar. We can include, within those natural convection, that still air study gravity as well as an ambient temperature. And this, will drive or, will be used for those calculations of the thermal study. In addition to the DCIR data that I was talking about already, we can also, for convection studies, include power dissipation values for components specifically. So this is an added benefit for those users that are looking for not only via trace and plane thermal, but also thermal on the components themselves. So if you have a known efficiency for your components, you can go in and set those power dissipation values. And the nice thing about, again, bringing in an ODB++ or an IPC 2581, the 3D geometries that you would be creating for your components within tools like Altium will come through within the length, width, height of the components here in this Icepak simulation. So those import over very smoothly. And again, a user can go in and define the power dissipation on each component or on a group of components. The other thing that I think is kind of nice about this too within SIwave is that the Icepak tool, as you can see towards the middle of that dialog box, there's an estimated PCB temperature without heat sinks. So what this will give you is an approximation of what SIwave believes the max and mean temperature for your PCB, with or without components, will be for this study. So this gives you some insight, obviously going in. If you go in and see a max temperature, let's say that's 300 degrees Celsius, right away there's a very good chance your component is going to fail, or your board is going to melt. Something catastrophic will happen well before it gets to 300 degrees Celsius. And so, this gives you an understanding of, okay, yeah, I don't even need to simulate this, from a thermal perspective, because it's going to fail. Or did I make a mistake somewhere? Usually it's the latter. Usually, you may have, someone may have, instead of putting, 250 milliwatt, they may have put 250 watts for power dissipation. Just something that you can easily fix and check before you go into the full Icepak solve. What I've got next for you is an example of those results. So this is something that you can get within Icepak within SIwave. And so this is a nice view here of those component level dissipation values, as well as the thermal from the DCIR. So both of those being combined together to provide this heat map, this contour plot for you. And as I was alluding to before, there is a nice update within 2021 R2 for SIwave and Icepak. So before, what you would have to do is you would have to install Icepak Classic, which comes within the Fluids package installation, to use Icepak within SIwave. That's been replaced. Now it falls within the electronics, which removes the need to bring in or install another package. So it's just a very nice fix that Ansys has added here within the tools. And now you can also import. You've got a nice transition from the SIwave UI and then bringing it directly into Icepak in the electronics desktop. So you can simulate, as shown on the left, the components, the heat sinks. But if you're wanting to get into more complex structures, Icepak in the electronics desktop or Icepak ADT allows you that freedom to do so. All right. So meanwhile, let's talk a little bit more about power integrity, and specifically within capacitor optimization within SIwave. So of course, we've already covered steps 1 and 2, importing in the ECAD and looking at the component mapping. The next thing that we can do is perform what's called an SYZ simulation or SYZ extraction. So this allows you to understand over frequency how your planes, as well as with capacitors, inductor parasitic values for VRM, as well as other components on the board from a frequency domain perspective. So we can simulate this and provide information for your board. This is a simulation representation of your board that then can be used for other solves down the line. So what I'm showing on the right here is the setup for that. In this case, a user would go in and assign ports. There would be a very small port impedance, representing very close to what you would expect to be seeing as a matching. And then you can go in here and define the frequencies. Traditionally I see values between DC and a gigahertz, but you can go in and change. The other thing I want to talk about is there's both a discrete sweep and interpolating sweep. Of course, I'm going to recommend that users use the interpolating sweep. It is significantly faster as you are simulating a handful of points and plotting from there, rather than simulating independent points, which can get pretty time consuming. Now, again, the other thing that's worth touching up on here too is we can include in the other solver options within this, including parallel processing using HPC packs. You can really run simulations rather quickly for this SYZ extraction when you speed up with multiple cores using the HPC packs that Ansys sells. Here's just an example of a very simple SYZ plot. I just wanted to include this just for some of the users that may not have seen this before. And this goes through, again, the plot of, in this case, a rather simple PCB over frequency. So this is what we would use and design around for decoupling capacitor, placement and optimization of those. The next thing I want to jump to is resonant modes. So when we're talking about, in this case, power integrity, resonant modes gives you insight between coupling on planes, on layers, and it can give you a glimpse into where you may have higher than expected impedance on these different layers. Now, this is very impactful with your designs because this shows you specific areas where you may need to improve your overall design. Between ground and power planes, this can be an issue when you're designing that PDN. And, this is something that, again, a really quick to set up simulation. In this case, there doesn't even need to be ports defined. This simulation just is requiring your ECAD. And I'm just going to show you this just so you have insight into, how easy it is. You define the frequencies, a minimum frequency and a maximum frequency, and then the number of modes. And then you launch it. This is it. This is all the setup is required. And the results here, as I'm showing now, go in and you can go in and plot the coupling between layers. And as you can see, there are multiple modes being shown, and you can animate and see over phase how those modes and how those impedances differ. Of course, at frequency, as shown above. So the modes, both the real and imaginary frequency, and then, you can change which mode you're looking at, and you can plot, and you can create animations that you can put into a presentation just like this. So the last thing that we are going to cover today, and I've left myself just enough time for this, which is great. We're going to talk about the PI advisor. So this is the workflow specifically within the PI advisor. So this will take you through the setup for optimizing decoupling capacitor decoupling capacitor values, and it will take those Z parameter data, and along with rules and limit lines that a user specifies, you can then design around those limit lines. So, the first thing is exactly that, going in, taking the SYZ extraction, in this case that Z parameter, and then a set of limit lines that the user can go in and input. So you can, of course, manually go in, type these in. You can also import in data files to be used for this. So if you have a set of requirements for your devices, you can repeatedly use the same file and save yourself a little bit of time of inputting those in. And you can, work to design around this. The goal here is to make sure that that Z parameter is meeting the requirements set, again, by the user. So we can go in and select the capacitors we're looking to optimize. Now, of course, when we take this library, this is not the library. If we go and take the all of the reference designators for the capacitors, you don't always have them all on the same power plane or power delivery network. And so you may not want to select all of these. In this case, I selected a handful of them. I just wanted to make this caveat just to make sure everyone was aware. And we can now design and optimize those values, again, to try and meet the requirements of the Z impedance that we saw in the prior slide. So here is that PI advisor setup. Again, this is going through setting that impedance, capturing that impedance in that Z extraction over frequency. We have set those capacitor reference designators we want to optimize, and now we can go through and we can tell the tool the parameters or the bounds within that optimization. So there is again, using the library of components, we can select components we would want to potentially use. We can also go in and select and filter those depending on things like size, value, range of values. And so there is a host of different things that you can modify here while you're doing this optimization. Now, again, what's nice about this is the computer, instead of a user going through selecting one capacitor, changing it, resimming, changing it, resimming over and over and over again, or even worse, going to the bench, measuring, desoldering a capacitor, soldering a capacitor, measuring, desoldering, soldering over and over and over again. This is something where the software itself can go in and do this rather rapidly. So a lot of different values, in a lot of different capacitors here. We can have multiple reference designators, as you see on the left. And this is something where a user can save themselves, a host of time by letting the computer solve it for you. So here's an example of some of those results. So what you would see is a number of different schemes. You would have what's called a quality metric. This will tell you how well it performs compared to the user-defined criteria. And in this case, it's showing 8 different schemes. Each one of those would have different capacitors from the list that you've selected or filtered for each of those reference designators you told the software to optimize. And then on the right, it's going to show you exactly the performance, in this case over frequency, of that new PDN. So, this again adds a lot of strength to anyone that's looking to design their power delivery networks. The nice thing about this is you can take these results and you can bring it now into a circuit tool, and you can simulate, and you can do, not only checking, from a frequency domain to see how well the results align, but also from a transient domain, you can simulate to see how good the performance or the ripple is of your signal, of your voltage. So in this case, I've done exactly that. So I've gone in here, I've taken this output, this touchstone data set. I have added a little bit of a more complex structure here. And we're going to be looking at this again over frequency. It's really no surprise here. The performance is nearly identical to what we saw within SIwave. And this is a nice check. But what's really I think a bit more interesting here is that we can now look at this from a transient. So we can then add a load to this, as well as the voltage signal. Set this up within the circuit tools to represent what we have on our PCB. And we can see here, and this is just an example of a load voltage, but we can see here the performance of that now over time. And so if we had some spec for ripple, we can see that it's meeting, if it was 50 millivolts, for example, this would show that it is meeting that spec for ripple. And that's really the strength here, going from, those beginning steps to the, final step here in the transient. We can take all of those steps early in that design, making sure we're optimizing those values, and we can improve these designs here and get to this final step, this output. It seems like a lot of different steps to get there, and there's insights along the way. But this again is the output for most people that they're interested in, outside of the impedance over frequency. This transient waveform really at the end of the day is going to tell you, is this going to provide a stable voltage to your IC? So just to kind of wrap everything up here nicely, about 5 minutes before questions. But PCBs are becoming more and more complex. I don't think anyone is surprised by hearing that. This tool, SIwave, has a lot of features in it, but today specifically talking about power integrity, there's a lot of ways that you can improve your design, both from an electromagnetic standpoint, as we talked about here at the end, but also from a thermal perspective. If we were looking at meeting requirements for thermal, we could design around those. Of course, we didn't even talk about optimization within the thermal tools. I just wanted to, discuss that it's there, and that users can really bridge those gaps between electromagnetics and thermal. And this is nice here because it's not just optimizing those electrical designs; it's optimizing that system. And so, when we're talking about these very complex PCBs, we need to ensure that they're going to be reliable. And really, these tools allow the users to build their PCBs with confidence and make sure that they are performing as expected, and really, save time and money on those design iterations.